Allora. Dai, ci siamo quasi. Ci siamo, mancano ancora qualche minuto. 51. Vabbè, intanto iniziamo in italiano. Grazie per essere venuti. Aspettiamo ancora qualche minuto perché poi inizieremo la diretta sulla nostra web TV e anche sul canale TV sempre di Science. Quindi tutti pronti? Ditemi voi quando. Sì, ne approfitto per darvi alcune indicazioni di sicurezza e pregherei di non ostruire le uscite, le scale, di lasciarle libere, e le uscite di sicurezza sono all'inizio della scalinata e dietro del palco. Questo è un obbligo farvelo sapere giustamente per qualsiasi evenienza. Grazie. Iniziato, ok, però aspettiamo ancora qualche minuto. Ancora qualche minuto per non iniziare troppo presto rispetto a Science. Andiamo, aspetta un secondo. Ok. Good afternoon, ladies and gentlemen. I'm Giuseppina Piccirilli, the head of ASI Press Office. The Italian Space Agency and I are very pleased to welcome you to this press conference. First, I would like to remind you that you are currently live on our web TV and on Science Magazine television channel. So I would also like to extend our greetings to the people that are currently following us on stream. You are here today to announce the new discovery, a stunning revelation about Mars, published on Science magazine, made by a team composed of researchers Enrico Flamini, Elena Pettinelli, and Roberto Rosei, belonging to Italian Research Center and the universities. They are here today to present their findings. These are results of a study from the Italian radar MARSIS on board the ESA Mars Express probe. The Italian Space Agency managed its realization from the beginning until today. It stands as one of our greatest successes. So now, before I introduce our first speaker, I would like to let you know that we are going to share this amazing discovery with our social media accounts using the hashtag #MarsisNews. And now let's start the conference with Enrico Flamini, former chief scientist of ASI and planetology professor at University of Chieti. Please, Enrico.
Non so se posso parlare, questo è il mio problema. Ah, si può parlare? Ah, scusa, va bene, perché mi mancava... quanto manca? Ok, 2 minuti è un tempo infinito. Come diceva Einstein, se stai con una donna 1 minuto è poco, se stai su un termosifone è tantissimo, se ti siedi con un termosifone, non passa mai il tempo. Sì, appunto, è così anche la barzelletta. Oh, okay. So, we have still 1 minute or so. As Einstein said, 1 minute with the beautiful women pass too fast. 1 minute over an ether can be an incredible amount of time. So, I mean, at the moment I'm on an ether, to be honest, waiting for the right time. Okay. So please have the time to sit and enjoy, and I hope that you're going to enjoy what we're going to show you in now 30 seconds or so. Okay. Well, thank you all. We are here today to present you our results and the fact that we have found liquid water in on the subsurface of Mars. This is a work that has been done by a team that is formed by a lot of people, as you can see, 22 persons actually, and 3 of them are on the floor now and will present you. The other are sitting in front of me and coming from different Italian institutions, and some young, and so very energetic, very capable to go and to remain on analysis of data up to very late in the night. Some a little bit older, as myself and as Marcello Colladini, all the Martian guys. And but the mixer of experiences, the mixer of capabilities, in the sense that engineers, geologists, physicists, planetologists as myself, This is what provided the right amount of capability inside this team and led us to success, jointly with an extremely nice way of dealing with all these people. A very good team, a very not professional is not correct in the sense that obviously is professional, but a friendly team, and a way in which you can discuss even in a very harsh way, but always finding out a solution. This is an essential element, as the capability to remain on the piece, to be stubborn, as we could say, and working hard for many years. In fact, the first evidence that water was largely present in the past on Mars last the times of the Viking mission, so almost 40 years ago, when there was the evidence that lakes and rivers, deltas were present on Mars. Here we see, for example, an example of what is a Madeline Valley, that is a long river, 600 kilometers in the length, and is actually a long channel that eventually is draining into the crater, the Gusev crater. Well, for this reason, what we see today, that is a picture in which water is mostly present as ice on the surface in a north polar caps and in the south polar cap, and also is present as permafrost, so mixed with the soil again in an iced form. And the fact that for sure in the past most of the water has been swept out by the solar wind, and provided us the idea that, as in other planets, and in the case of the Earth, for example, some of the water that was once present on Mars should have migrated to the subsurface and eventually remained trapped there, possibly since the time when Mars was wet on the surface. So something that is indeed was this the real question that we had: where the water has gone, where the liquid water has gone? Is only in the ice form? Is only the one that Mars has lost at a certain point in time, or can be still hidden in the subsurface? And that's the reason why on December 1996, when ESA announced during International Mars Exploration Working Group meeting held in Cocoa Beach, the intention to realize Mars Express, an F mission, a fast mission, a low cost, ASI proposed to include on the side of the other instruments that were actually belonging to a former mission that was lost, Mars 96, the Soviet Mars 96 mission, to include also a completely novel instrument, never flown before, and with no previous experience in analyzing other planets, but based on a very strong competence that we had in Italy for the radars, and that also we had with our friends on NASA side that supported us in the realization later on. And so this is MARSIS presently. Is a sounding radar, a low-frequency radar, capable to penetrate into the Martian surface, that I want to like to remember this dry and very cold, two essential points that I think later on Elena will explain better, and search for water in the depth. This was our idea. The Mars Express was launched in June 2003, arrived in the same year on Mars, but MARSIS started to operate only in July 2005. And the reason was that we had to open the antennas. It's 40 meters long booms, very light, but also that during the aperture could have flexed back. I mean, could have opened and then flexing back to the to the spacecraft. So in principle, could have jeopardized some part of the spacecraft. Then 1 year we spent, and 1 year has been spent by our colleagues of JPL that provided us the antenna to analyze any possible condition that could have jeopardized the Mars Express mission. At the end, it came out that there was no harm, and finally the antenna was open, and MARSIS started to work. Well, MARSIS was conceived by Professor Giovanni Picardi, one of the utmost excellences in Italy and in the world for what concerned the radars, and realized under ASI management by Thales Alenia Space Italy, while the contribution of JPL and through a NASA agreement, ASI-NASA agreement, was for the antenna, and from Iowa University for the what concerned the radio frequency receiver. Giovanni Picardi was, of course, the first PI of the mission, with Jeff Bloth as co-PI, and with Roberto Rosei, that is sitting here today with us, as deputy PI. When Giovanni passed away, then Roberto became the PI. ASI is still managing the science contract in Italy, and I'm very happy to see in the audience the present manager for this activity. From July 2005, MARSIS has operated flawlessly, providing an enormous amount of data and the coverage of most of the Martian surface, making a lot of discoveries. I want just to mention one. I mean, it's difficult to mention more, and there is no time for a talk on MARSIS discoveries. But, for example, the thickness of the South Polar Ice Cap, that jointly with the our radar around Mars, that is Charade, that measured the same in the North Pole, for the North Pole, provided us even an estimation of the total amount of water in the ice. But MARSIS was a novel instrument, never flown before. And we have also to discover not only its potentiality, but also how to evolve the processing of its data. And this was maybe the most challenging part of all the activity that led us today to the result. We have afforded a lot of major challenges, solved them, and in particular the one that was needed to determine the dielectric properties of the unknown layers in the depth, that now we may say is water. Then I leave to Elena the floor for going on in the details of this.
Okay, thank you, Rico, for the introductory part of this discovery. I'm going to show you briefly what is the principle, the physical basis for the measurements. So this will help Roberto to explain the findings of this research. So how a radar works in a simple way. So you have an antenna that sends electromagnetic waves down. Okay, when the electromagnetic wave impinges on the surface, can be reflected back, like in this, and a part of the energy penetrate down to another interface and got bounced back and got gathered by the antenna. Okay, so if you have a layer structure, like in this case, what you recorded in the antenna, essentially, you measure the two-way travel time is the time that the impulse takes to arrive to the interface and comes back, and the amplitude of the signal. Okay. So, big question: why is the radar sounder the best method to look for underground water? Okay, we know this since probably the 50s on the Earth, and I show you this because these are the two extreme but best environment for propagation of the electromagnetic waves at radio frequencies, so in the megahertz on the Earth. One is a very dry environment, and another one is a very cold environment. Essentially what we would like to have as a material to investigate the depth, what we would like to have is an electromagnetic wave that impinges on the surface, entering the second medium and propagate without attenuation, so with the minimum attenuation possible. So we have to search for areas, for example, on Mars, where this technique can be successfully applied. And there are several areas on Mars where we can apply the radar, of course, and that's why it was designed and made. One is some dry areas in some part of Mars, and the other important part are the polar caps. And we know that the polar caps, we knew before MARSIS start to collect data, that the polar caps are mainly made by water ice with some layers on top of CO2 ice. So this is a great environment to apply the radar, and in particular ice. Ice is a very transparent medium, especially if it's cold and pure to the electromagnetic waves. So it's a good technique to apply to the Martian polar caps. Of course, these caps can have some impurities, but definitely the ice is colder than the ice on the Earth. And as I show you shortly, this technique has been successfully applied on Antarctica and Greenland. So we thought that this is a good analog for Mars environment. So how can we detect liquid water below Martian polar ice using the sounder? We use the technique of radar, but how we in some way guess that below some part of the South Polar Cap in Planum Australis there was water. And we rely on the fact that some physical properties that we can measure with the radar can tell us if it's a rock, if it's saturated rock, if it's sand, or if it's actually water. In the Martian frequency band, which is between 1.8 and 5 megahertz, you can see from this simple graph of the electric permittivity, this is the real part, but it's enough to understand the concept. You see that the permittivity of the water is very high, is about 80. The permittivity of saturated sediments, so sediments where in the pores or in the fractures there is liquid water, is about 23 or 25. And the dry rock is quite low, on average, let's say 6 or 8. And ice is even lower. So we rely on these differences to see contrast in the electric properties and investigate the subsurface in this way. So if we have, for example, ice on top and rock below this layer of ice, the electric contrast is small, the reflection coefficient is small, and the amplitude is small. You can see here in this simple sketch that the reflection coefficient between the atmosphere, let's call free space, and ice is basically the same as ice and rock. But if we have saturated sediments with water, you see already that the reflection coefficient is higher, and in a simple consideration, for example, not taking into account the attenuation, you see that the amplitude is growing. And if I go on and I consider a layer of water below the ice, you see that the amplitude of the peak is getting even larger. Okay. So this technique has been extensively applied since the 60s on the Earth, and has been applied especially as I said, in Greenland and Antarctica. You see a drawing of some of the lakes that has been found in Antarctica. You see how complex is the hydraulic system below the ice. And some of these lakes have been detected with the same technique, using a little higher frequency, but the concept is essentially the same. So what we would like to see, and what we use to detect and guess, let's say, we say calculate, what was the dielectric constant of the reflection, is explained in this sketch. So you have the radar that sends pulses, and pulses bounce back from the surface, penetrate into the ice, and got reflected by the rock or the bottom material below the ice. And you can see here this is summarized what I was showing before with about the dielectric contrast, that here the amplitude is small, here increase a little bit, here is very large. Okay. If we look at one moment at the real images collected in Antarctica, you can see clearly that the radar images give well-defined information about what is below. So this is the layering of the ice deposited in time. This is basically snow that becomes ice in time. This is the bedrock. You see this flat part, and you can see on the left the sketch that interpret the radar image. And you see quite well that this flat part and a strong reflection is the water, and you can see the bedrock around. Now, what we really have with MARSIS. This is what you have with data, and you will see that this is just an oversimplification, but we don't know anything. We record these traces, as I said, two-way travel time and amplitude, and we have these traces we can align due to the position of the orbiter. So what we can say a few things. Definitely, here there is the surface, so we can know, we can measure quite well from the altitude of the spacecraft, and we see now something different in different areas below the surface. We see this amplitude is low, this is medium, this is very high, okay? So we know that these amplitudes indicate a contrast in the electric properties between the materials above, the material above and the material below, also in different locations. Okay, so we can say probably here there is an interface, a subsurface interface. Now, let's look a little bit more in detail, and this introduce the part that Roberto will tell you about the analyzing and results of the data. So we know from other measurements that this is water ice. We knew from before, and there are other experiments or measurements that confirm this during the years and the missions. We should say that this is very simple. And you will see in the presentation, Roberto, that the traces are much more complicated than this. And what we have to do, we have to analyze these pulses, the feature of these reflected pulses, and extract, trying to find a way to process the data, make modelings, invert the data, to say what is the dielectric property here, here, and here. And this is what we have done with the analysis of the data. Please, Roberto, if you want to.
Thank you, Elena, and good afternoon. It must be obvious by now, because of the explanations given by Elena, that what MARSIS has been looking for in trying to detect water under the surface of the Martian polar cap is strong reflections from the bottom of the ice. Now, these strong reflections were found already in 2007. The figure shown here is made by two panels. The top one is a radargram, so a vertical section of the Mars polar cap obtained by MARSIS. The bottom one is a false color representation of topography. But the interesting thing here is that you see the surface reflection as the bright line in the upper part of the radargram, but also highlighted by an arrow, a strong, bright white line that represent very strong echoes coming from the bottom of the ice, echoes that are stronger than surface echoes, as Elena also pointed out in the case of liquid water. Was that liquid water? At the time, it was concluded that the answer was no. And the reason was that these strong reflections were localized exactly under the residual polar cap, the only part of the southern polar cap that remains frosted white throughout the Martian year. And the reason for that, for the bright reflection, was not really that there was some high permittivity medium under the ice, but rather than the residual polar cap was made of CO2 ice, which is a very transparent material. So the reason for the strong ecos was that a lot of energy was able to penetrate into the ice, propagate to the bottom, and produce a comparatively stronger eco simply because the pulsing pinging on the bottom of the ice had a higher energy. And so this essentially concluded the first phase of the search for water on Mars. But not everybody was content with this explanation, and the search continued outside the residual cap. And thanks to the effort of our colleagues, several locations outside the residual polar cap were mapped in which the strong reflections could be observed. The problem was these areas were very scattered and of a very small extension. Sometimes they seem to be of the size comparable to the footprint of the radar. And most important, the measurements over the same area in different orbits could yield different results. So the problem was a problem of scale, a problem of resolution, but also a problem of repeatability. Here we have a blow-up of a radargram, so we are looking much more into the detail with respect to the previous figure over one of these bright areas that can be seen in the center right of the image. So in this case, the resolution of the radar can see only a single pixel, even if this is not obvious in the image as it is shown here, but it's essentially 1 pixel across, in which the basal ecos are stronger than surface ecos. But then again, in another orbit over the same area, we might as well see that the bottom of the ice would be much less reflecting. So what the problem we found out later was due to the fact that we were forced, the instrument was forced to do a lot of onboard processing to reduce the data volume that was sent to the spacecraft. The spacecraft could tolerate over only a limited data rate from the experiment. So what was happening in the instrument was MARSIS collected 100 or even more pulses, and then it would sum them together and send the result to the spacecraft. The problem was, because these bright spots were relatively small, when you sum together many pulses that come from unremarkable areas in which the reflections from the bottom of the ice are weak, with few pulses in which the reflection is bright, you essentially cancel the strong reflections. They get averaged out. This problem was solved thanks to the effort of our engineers by bypassing the onboard processing. And thanks also to the serendipitous choice of adding extra memory chips to the instrument, it was possible to store raw data before they were processed by the spacecraft and downlink them to the ground at a later time. If you do that and you look at the same data, at the same area, you get something like this. And now many more details become visible. And now we see the layering much better. We see its lateral continuity, and those areas that are highlighted in blue are those in which the reflections from the bottom of the ice are much stronger than the surface ones. And this time, using these data, we were able to achieve repeatable observations. By flying over the same area, the bright reflector would be there time and again, every single time. That really was the change that propelled us towards our goal, demonstrating the presence of liquid water at Mars. However, that would not be easy. It would take 2 more years after we finished collecting the data before we could make it. Now, this is how the analysis started. You can just see here a commented version of the radargram. So the bright line here is the surface reflection. The layered structure between the surface and the basal reflection is the south polar layer deposit, so the layered structure of the ice. And in the bottom panel of the figure, you see also power, eco power for the surface in the red line, and from the bottom, from the base of the ice as a blue line. And you can see that sometimes the blue line, as I was saying before, crosses and goes over the red line. So these are the strong reflections that we observed. the good news was then that we were able to map these bright reflections. However, we could do it over a very limited area because this raw data collection mode limited strongly our capability to observe. We had only short stretches of data collection. And now we found this particular place that was already suspected to harbor, let's say, to have bright reflectors in it, which is mapped over a mosaic of the south pole of Mars. So the gray square encompasses a false color map of basal reflectivity produced using the 27 observations we have available and shows in false colors the brightness of the reflection from the bottom. And of course, the blue area, is the one that has the strongest reflections. So this is a blow-up of this image. You can see that we have a clearly well-defined maximum that is seen across several orbits every single time. We have weaker reflectors all around. Some of them approach this central very bright reflector, but only, let's say, we are confident of our observations only for the central part because the number of repeated passes over the other areas is smaller. However, when we analyze this area, especially the bright reflector, we find that the topography around it, the basal topography, the topography at the bottom of the ice, is that of a basin. So the bright area is also a local depression, surrounded on three sides by higher terrain. And this also contained, in our opinion, a clue of what the nature of the bright reflector was. Water tends to collect in lower topography. So this also I'm showing here some quantitative analysis of the result and compare it to observations done on Earth. On the bottom right, you see the same panel that was shown before. On the bottom left, you see radar data from Greenland, so acquired on Earth. And you see a radargram, in spite of the false color, the information is similar. You see a plot of surface and subsurface echo in similar color, and you see areas where you get these bright reflections, even in the Antarctic. And if you somehow plot an histogram of the power of the reflections inside of the bright reflector and outside of it, you get two very different histograms. Of course, on the right side, this is done for MARSIS data, and the orange histogram is for areas outside the bright reflections. The blue histograms is for the area of strong reflections. And on the Earth, you get the same. If you do the same operation that was published independently way back in 2008, you get a completely similar behavior of the power of the echo. And even the distance, the difference in power between strong reflector and surrounding terrain is similar, around 15 dBs. So we get something that on Earth is really linked to the presence of liquid water. Now, the problem was, it was not, as it was found in other places on Mars, that an alternative explanation could be provided by the presence of certain different ices, CO2 ice in particular, on the surface. We had to go through a very extensive effort of modeling what the response of a complex stratigraphy and mostly unknown stratigraphy would be to a radar pulse, depending on what was lying beneath. And to conclude, to summarize the result, this illustration here shows the same radargram that was contained in the previous figure for MARSIS, so the eco power distribution, but also on the right side, you see the corresponding distribution of modeled basal reflectivities. You see that outside the bright reflector, the basal the permittivity is mostly in the range of 5 to 10, which is typical for terrestrial rocks, whereas inside of the bright reflector, you are well above 15 for the majority of the data. So this was our conclusion. We saw that the bright reflections we were observing, no matter what you think is within the south polar layer deposits, might not be explained by dry material. We came thus to the conclusion that the only possible explanation for the bright reflection was the presence of liquid water. Thank you. And I would like now to leave the floor to Enrico for final remarks. Thanks.
Well, the final remarks are very simple. Water is there. We have not anymore any doubts, after many years of doubts, that we have to remove one after the other up to today. And now I would like to pass the floor to the ASI president that is in Kourou for launch another satellite, because we come from the past and we want to go to the future, and who better than the ASI president to say something on this. Please, Roberto. Can you hear us?
Yes, I do hear you. Hello.
Hello, the floor is fully yours.
Thank you for this connection. I'm at this moment in Kourou, where we just launched an Ariane 5 with 4 Galileo satellites on board from the European spaceport here in French Guiana. The launch has been really great, so I'm really pleased to have this opportunity to shortly comment with you this extraordinary discovery of the water on Mars. I think what has been done with the observation which has been just published is really amazing. We knew that Mars, about 3 billion years ago, was full of water, and something has happened in between, and most of the atmosphere and the water with it has gone. But we know about the ice, and with this observation by MARSIS, we have evidence that below the ice, deep below the surface of Mars, there are lakes and great quantity of water. This clearly is exciting, because we know that water is almost everywhere in space, and we have a proof on our planet that where water is abundant, life can prosper. So we are really excited by the fact that there is still a large amount of water on Mars, because we are working on this ambitious mission with ESA, ExoMars 2020, to drill the surface of Mars a couple of meters down, and hoping that we can tap some of the ice or the water to analyze it. And because clearly the opportunity to study water underground give us the hope we can find something interesting, something important about possible life on the red planet. If the water is everywhere in the universe, and if the life is very much connected to water, then we can hope that life is also almost everywhere in the universe. And the closest place we can check is exactly the red planet. So this discovery, which has been contributed with the Italian technology of the sounding radars by the Rome and Professor Picardi tradition, are really a great step in the direction of a new way of looking to the red planet. This is what has been presented today is really a grounding, the foundation of the new approach of studying in detail what the red planet still is hiding below the surface. So I really happy to represent the Italian Space Agency, which is invested so much in this important satellite, this mission, Mars, the MARSIS antenna, and we consider that again one step on the long journey, and the international collaboration which has allowed for that, and the friends and which are gathering in Rome and over other places in the world to announce that to the scientific world is making us proud, and we like to thank whoever has contributed for the design of the experiment, the operation of it, and most important, the scientists which were able to detect this faint but very clear signal, because this gives us hope, give humanity hope that we can have even more important discovery waiting for us in the future years. Thank you so much.
Thank you, Roberto. Thank you for these words. Indeed, we had spent a lot of years, and thanks to the Italian Space Agency, we were capable to do our job. And because Mars Express will last a little bit more, I hope that you are going to continue as a... Well, I have changed my hat in this sense. I've been ASI personnel up to a few months ago, but now I have to looking at the things a different hat. And I hope that MARSIS can continue to operate on the wave of this success.
Absolutely agreed. I think the delivery so far has been good, so let's keep going.
Bye.
Bye-bye. Thank you.
Okay, thank you to our president, and above all, thanks, of course, to all the scientists that have been with us today to talk about this amazing discovery. Now, we would to give you the chance to ask to all the scientists some question. I would ask the journalists to introduce themselves, starting the name and the press affiliation, please. No one? All was clear?
Well, astonishing. We are being really clear.
Oh, yeah. Oh, yeah. All was clear for all people. Okay. There is one? Okay. Paolo Riccibitti.
In English or Martian or Italian?
Martian, please.
La domanda che viene subito, the first question is about the life. This discovery permit us to think about what kind of form of life. I ask to all the three science.
Oh, no, abbiamo gelato. You have another one. Okay.
So we can sit and
Paolo Riccibitti, Il Messaggero.
Thanks.
Okay, what with this instrument we may say is there is water. The water is screened by the solar, the cosmic radiation and solar radiation, is liquid and is salty and is in contact with rocks. There are all the ingredients for thinking that life can be there or can be maintained there if life once existed on Mars, a Martian surface. However, MARSIS cannot say anything more, so we may guess about what are the conditions there and if the conditions are favorable or not, but is not this instrument that can directly answer the question if life is there. I don't know if...
One? No. Okay. All is clear? Thanks a lot. No, there isn't one.
Just a curiosity. How big is the minimum size of the region in kilometers? Or?
The patch, the blue patch on the figure that was shown before, is about 20 kilometers across. The thickness of the lake is difficult to determine because the radar is not able to penetrate below the surface of water. But as a minimum, it has to be of the order of 1 meter. This is because otherwise the radar would just see through the water, not see that. Which amounts to, by some back-of-the-envelope computation, still to several hundred million cubic meters of liquid water.
Roberto, maybe I missed in your presentation, how deep is below the surface this body of water that you have detected?
I'm afraid I didn't say it. I was too excited. And the answer is 1.5 kilometers.
No? No, not all one. Non sapevo. No? Okay. Okay. Thank you. Thanks a lot, all of you. And thank you to the Science TV program. Thank you for ASI TV. Thanks to all of you.